Here's a solution to the quiz from from Halloween. So I had a lot of comments on this quiz just about the difficulties of dealing with this extra little parameter here, this k. The k caused a lot of problems. So I think that, it's important to understand how to do problems symbolically in terms of constants because it allows you to sort of tackle more general situations. For example, one problem might have k equal to 2 and another has k equal to 3, but sort of by leaving this constant as k, you're able to solve both problems simultaneously. Now, the trick to dealing with constants, I think, is to go through the computation, pretend that it's equal to 2 or something like that, and think about what you would do. But instead of writing 2, write k. So let's go through this example and kind of illustrate that approach. So first of all, we have this function here. Question A is just determine all critical numbers and inflection points of A. Right. So in terms of critical numbers, we know that critical numbers are solutions to the equation f primed of x equals 0. So if I look at my function here, to differentiate a function like that, we would want to apply the chain rule. So we want to think of this as f of u, or e to the u, where u is negative k x squared. Right? So the derivative would be du dx times this function df du. Right? Now, just thinking of k as 2, right? If this was just a constant, I would just bring down this 2 and use the power rule here, and that's it. So the derivative of u is just negative 2kx, and then e to the u, the derivative is e to the u, so negative, excuse me for a moment there, a little bit of a mishap, negative kx squared. And to figure out the values of x for which this is 0, well, let's think for a moment. So this guy right here, right, this guy is never 0, so all I need to do is set this guy equal to 0, and clearly there's only one solution for that, right? Which is when x equals 0. So there's our only critical number, right? So to determine the inflection points, we just look at the second derivative now. And for the second derivative, we need to apply the product rule. Excuse me, my screen goes a little haywire sometimes. So for the second derivative, we apply the product rule, thinking of this first function here, f and g. So we take the derivative of f, and remember, k is just a constant, so the derivative would just be negative 2k, right? And we multiply that by our second function. And then we add to that, we keep our first function fixed, and we redifferentiate our second function, which we already did once, and receive this. So our inflection points are solutions to f double prime is 0, but let's simplify this before we do that. Notice that both of these terms have a negative 2k e to the negative kx squared in common. So if I factor that out, what I'm left with is 1 minus 2k x squared, right, from factoring out those terms there, right? So now setting this equal to 0, again, this first term right here is never 0, so I just need to figure out where is this 0, and it's pretty easy through some simple algebra to see that that yields the solutions. X is plus or minus 1 over root 2k. Okay. So once we've completed this task, the next step is part B. We want to identify or just classify all the critical numbers as either local max, local mins, or neither. And there's two ways to do this. We could use the first derivative, right? And we could say, well, I know that f prime is 0 when x is equal to 0. And when x is less than 0, well, if I go back up to my expression for f double prime, I plug in x less than 0, I get a positive number here. Whereas if x is greater than 0, right, I would get a negative number. So the picture here is if I was looking at f, right, f would be increasing and then decreasing, which means this should be a local max. Okay. Alternatively, you could use the second derivative test and plug in x equals 0 into the second derivative, right? So we could look at f double primed of 0, which if I plug in 0 for x here and 0 for x here, I would get negative 2k, which is also less than 0, which yields concave down, which implies that we have a local max as well. Right. So finally, let's just sketch a brief graph, summarize the information we have here. Right? We've said that this function has a max at x is equal to 0, and if you actually plug in 0 to the function, it just has a max at 1. It has inflection points of 1 over 2k and negative 1 over 2k. Right? So I know it's going to switch concavity at those points. Furthermore, if we look at the sign of f double prime, right, looking at this function for f double prime here, if x is between these two values, then this term here is going to be positive and this is going to be negative. So I know that my function is going to be concave down right here, right? And I already knew that because I knew that at 0 I got a negative derivative. And then it's going to switch to being concave up. So the graph, assuming you're a better drawer than me, will end up kind of having this bell-shaped type curve to it, right? In fact, that's one of the reasons why this function is so important, because it gives rise to these kind of bell-shaped curves. And these inflection points in statistics end up being related to the standard deviation of the distribution that you're studying.